Hello class, so this is CSE-5250, Section 2, Week 12. Recall back at last week we didn't have any new content, so instead I opted to extend the due date for the first assignment so that it was due this Monday. So hopefully you've turned that in by now. With that out of the way, I like to start looking at NVIDIA CUDA. Not that you'll be programming anything with NVIDIA CUDA, on account of I can't guarantee that you have access to the necessary hardware, and the installation process does take a bit of time, even if you did have the hardware. But if you're able to follow along, then what you'll find is NVIDIA CUDA is one of the more powerful parallel processing options that we have available to us. So with that, I'm going to start looking at what the sieve of Eratosthenes would look like if we were to use NVIDIA CUDA. So, there are a few minor changes to this sieve compared to the ones we've programmed throughout the class. For one, this one only has one array instead of two arrays. We programmed our sieves to have two arrays. One was an array of numbers, and that was just to keep reference. That was just to keep track of the numbers that we had to go through. Technically, it wasn't necessary because this one only has one array. It is an array that has every integer from 1 to the maximum number we're searching for, and if we encounter a non-prime number in that array, we replace it with 0. Compared that to our sieves that we were using previously, we used that reference array of numbers, and then we had a separate array of bools that we would set to false for every corresponding number that was non-prime. So yeah, this one has a few more optimizations than what I had described throughout the course. And I guess that leads into one thing. If you're going to optimize a program, try optimizing it as much as you can before you consider parallel programming. Because at worst, parallel programming might make the execution time of a function even worse. But if you've tried benchmarking the sieve already, you may find that it may depend on the workload itself. Also, don't worry if you didn't get any speed up at all. It's more important that you at least tried. Anyway, let's look at this thing. First, let's look at this thing here, which is the function that's to be run on the GPU itself. This is known as a kernel in CUDA, not like the kernel in an operating system. You have to add this global tag right before it. But after that, we write it as we normally would any other function. So this is the sieve. We are taking in a list of numbers. It's actually an array. We have to also give it the search max, and for our purposes, I'm feeding it the square root of the search max. Now, there are 4 things in here, but we only need to worry about 2 of them for now. The first one is the thread number, and the second one is the thread count. So, that's thread idx.x and blockdim.x. This is basically equivalent to com size and rank and com size back when we were using MPI. So each thread has its own ID, and each thread knows how many other threads there are. There's also a block count and a block number. This is if you're to use multiple blocks, because threads can come in blocks, and each block can have its own ID. So this becomes important if you're using multiple blocks, but if you're only using one block, you only really have to worry about the thread count and thread number. Alright, so we enter the for loop here. This is the outermost for loop, and typically with the sieve of Eratosthenes, we don't have to go all the way to the search max. We can just stop at the square root of the search max. So, that's the outer for loop. We iterate from 0 to the square root of the search max. The num list is an array of numbers, as I said, and it's going to iterate through the array to find a number in that array that was not replaced with a 0. If it was replaced with a 0, that means that number was non-prime. If it's not, we say that is the current prime. At that point, we can enter the inner for loop, but we need to make a few calculations. First, we need to determine the start index for the current thread. Now, in the general case, this code that I'm highlighting, that's all you need. It's going to be, if you have multiple threads and you want to tell each thread a different starting location, as per the case, which is usual for these kinds of things, you want to give it a start index that is based on its thread ID. So for our case, that's basically the thread number. In the case where we want to work with multiple blocks, here's how it works. If you're to use multiple blocks on a NVIDIA CUDA function, if you want to enumerate each thread so that it has a unique ID, you add its thread number to the product of its block number and its thread count. So if you have 4 blocks of 256, you would have thread IDs from 0 to 1023. So if in block 0 you have thread numbers 0 to 255, block 1 would be thread numbers 256 to 511, and so on. Oops. Yeah, in the general case, this is what you really need, but in our case, we're multiplying a few more things to it. Here's how. So we get our starting position by finding this and then multiplying it. No, we add 1 to it and then we multiply it by the current prime. And that's our offset from the starting position, basically. And that's how we got our start index. If you want the stride, that's how much we increment by. It's going to be the number of threads that we have, the thread count, and multiplied by the block count. Now, there is one other optimization here, and it is this. We don't have to increment by 1 for the inner for loop. We can just increment by the current prime. But we can be even more optimized and say, let's increment by the product of the current prime and the stride. That way, the inner for loop only has to work on numbers that are multiples of the current prime number. That isn't the current prime number itself. That's what the +1 means. So basically what this is doing is, suppose we were starting at the number 3. The first thread will start at 6, the second thread will start at 9, the third thread will start at 12, and so on. That way, we'll have a situation where every number encountered by the inner for loop will always be a multiple of the prime number. That isn't already the prime number itself. So, if you're starting at 3, we do not want to eliminate 3 as a non-prime number. We want to eliminate all the multiples of 3 as non-prime. Right, so that's the sieve itself. We're going to call this in the main function here, and let's walk through that. Okay, so we have our search max, so we're looking for primes up to 10 million. In our case, we're going to use 64 threads, and for the sake of demonstration, let's use just one block of 64 threads. We have our stopwatch as we did before. Auto start time equals high resolution clock : now. I'm using namespace standard chrono just to keep things short. So normally it would be like standard chrono, standard : chrono, : high resolution clock : now. But if you add using namespace standard chrono, you can shorten it down to just this. Alright, so now what? Well, now we need to allocate memory. So if I hover over this, if you're using Visual Studio and you install the CUDA development thing, IntelliSense will update accordingly so that when you hover over CUDA-related functions, you get a description of what it does. So, allocates memory that will be automatically managed by the unified memory system. Basically, we're allocating memory on the GPU. I believe that's what happens. Anyway. Typically a GPU also has its own memory. So, you have to tell that thing what we have to tell the GPU what data we're going to be processing, more or less. Okay, so we allocate memory. We pass it the address of the num list. Technically, this is a pointer to a num list, but we need to pass it. We have to pass in the address anyway, and then we have to pass in how big is this thing in bytes. So we're looking for 10 million. We're looking for numbers up to 10 million. So our search max is going to be that times however big an integer is. So this is basically the size of the array in terms of bytes. Now, excuse me. This array, as I mentioned, is going to be containing all the numbers from 1 to 10 million. So I have to populate it. So for loop numlist I equals I plus 1. So that way it will have all the numbers from 1 to 10 million. The outer for loop only needs to iterate to the square root of the search max, so we have to find the square root of that. So whatever the square root of 10 million is, we store it in here, because we have to pass that later on. Now, numlist 0 is the number 1, and we have to mark that as non-prime. If we forget to do that, it's going to mark every number in the array as non-prime, and we don't want to do that. It nullifies the point of calculating prime numbers, because sorry, I'm just thinking. If you had to paint the house and the house is blown up, I guess you could say your work is done because there's no more house to paint. Anyway. Okay, now we get to the fun part. We call the kernel. See this triple chevron here that IntelliSense decided to break? It looks like the chevron and the less than sign, but it's really supposed to look like this. And on the other end, it's supposed to look like this. This is the execution configuration, and it basically tells the kernel how many threads to use. So, I mentioned that we had to set the block count to 1 just to keep things simple. So this is 1, and that says we only need 1 block's worth of threads. So really, we need to look at the second number here, and that's the thread count. So, thread count is 64, and we're basically using 64 threads to find prime numbers up to 10 million. So those are the first things you have to pass in. If you can call it passing, if you can think of these as passing these things as parameters, which I guess they're technically not, because they're not in the parentheses, they're in these triple chevron turn these triple chevron things. Anyway. Name of the function, execution configuration, and then the parameters. Those are the num list, the search max, and the square root of the search max. We pass those and we call the kernel, and then we sync. You have to call the CUDA device synchronize, so wait for compute device to finish blocks until the device has completed all preceding tasks. Oh yeah, these functions here can also return error codes, so in case you have something going wrong and you need to debug, you can store error codes in a variable and you can do debugging that way. In fact, if I'm to make a new project in Visual Studio 2019 and I said CUDA 11.6 runtime, a project that uses the CUDA 11.6 runtime. Next, let's just name it, let's just leave it as the default name, CUDA runtime, and create. If you decide to follow along with this and try it for yourself, and you installed if you wanted to try this for yourself, the website to download the NVIDIA toolkit is here. developer.nvidia.com/CUDA downloads. You just select what platform you're working on, your operating system version, if it's relevant, your architecture, and then you just download it, and the download is a pretty big file, if you ask me. But once you have that, and you have Visual Studio installed, and you create a Visual Studio project for NVIDIA CUDA, you get this default program. CUDA error_t is the data type for error codes. So, in case you wanted to debug, well, this default program has a lot of, it's got quite a bit of functions related to that, and, hold on, sorry about the interruption. Anyway, this is the default program that is provided to you if you're to use Visual Studio. Anyway, let's get back to the main program that we're looking with. So, okay, so we call the sieve, we call the kernel, and then we sync. If we ever have to debug, we can store error codes and debug with that. And once you call device synchronize, that's basically it. And then we can, that's basically it in terms of having the GPU do the work for us. At that point, we can calculate the execution time. Auto stop time equals high resolution clock : now. Then we calculate the execution time, and then we can print that out. And to show that the sieve actually worked, we can print out all the numbers. Just the first prime numbers, just the first set of prime numbers that are less than 1,000. And then after that, we have to call CUDA free, and this is to free memory on the device. Frees the memory space pointed to by dev pointer, which must have been returned by a previous call to CUDA malloc or CUDA malloc pitch. Otherwise, or if CUDA free has already been called before, an error is returned. If dev pointer is 0, no operation is performed. The device version of CUDA free cannot be used for the dev pointer allocated using the host API and vice versa. So we call CUDA free, and we just free up the memory. We pass in the we pass in numList, and that's basically the end of the program. Right, so if you're able to, try this out for yourself, but just in case, I'll just run it for you. And then we can do our own impromptu benchmarks as well. So let's run this and see how long it takes to look for prime numbers up to 10 million. 1.3 seconds. Let's try it once more just to make sure. 1.2 seconds. Alright, let's do an impromptu benchmark. I'll open up Visual Studio and document recovery. Close that. Let me just zoom in and one, 4, 16, 64, 256, and 1024. For the sake of comparison, let's just looking for primes up to 10 million and looking for primes up to, say, 10,000. Alright, so it took, what, 1.2 seconds on 64 threads, so let's just put in 1.2. Now, let's change this thread count to 256 and try it again. One point two, 1.17, 1.18. Yeah, let's call it 1.16. And that was with 256 threads, so let's try 1024 threads. The maximum, by the way, is 1024. I tried this on both my main computer and my laptop, and yeah, it's apparently the maximum number of threads is 1024. So if you tried any greater than that, then the sieve literally won't work. By that I mean, it won't sieve out. By that I mean, the function won't be called and you'll just get the array that you started with. So nothing will ever. So basically, you'll still get something printed out, but none of the primes were removed. So 1.26 for 1024 threads. So at that point, we're reaching the point of diminishing returns. 1.17. Let's call it 1.17. Right. Now let's go the other way and decrease the number of threads. Let's try 16. And it took 1.67 seconds. Alright, we'll enter that into the spreadsheet. Try it a few times just to make sure. Now, there is a way of automating this entire process by, you need to first build this program, but you can pass in parameters in the main function. So when you call the executable with the command prompt, you can pass in parameters, and that way you can pass in the thread count and the search maximum, so you can just, in theory, have a script that would automatically call the function over and over again, and you can even have it so that it writes the execution times to a file. That's just one way to automate this entire benchmarking process. So let's try 4 threads for now. And how long does it take? 2.97? 2.966, 2.97, wait a bit, 2.9. Let's call it 2.9. And if we just wanted to do 1 thread, what happens? Oh boy, it's actually taking a while. 8 seconds, wow. So parallel programming reduced execution time by a factor of 7? Yeah, about a factor of 7. Yeah. Roughly a factor of 7. So that took 8 seconds to execute on just 1 thread. Now, 1E7 is 10 million. If I type in 1E5, that's 10,000. So, let's redo the experiment with only searching for prime numbers up to 10,000. So, all the prime numbers less than 10,000. So, that took 857,000 microseconds, so 0.8 seconds. Run again to make sure. Hello? Not working. Let me try it. There we go. Yeah, 0.8 seconds. So, if I quadruple the thread count again, I get 4. .8 seconds. So 5. Yeah. Yeah, let's call that 0.75 instead. Increase the number of threads again to 16. Let's see what we get. .83, 0.74, 0.73. Let's call it 0.74. (16 times 4 is 64). So let's try it with 64 threads, as that was the default. 815. This is why it's preferred to do these benchmarks multiple times. So that way you can get an average execution time. So we're getting 0.74 again. So that tells me we're barely getting any sort of speed up at all. Presumably because we're looking for primes within such a short range, or rather, we don't have much parallel work to begin with. So that's why we're not getting much speed up at all. Okay, so one more doubling, and that's 256. Are we reaching the points of diminishing returns? Yeah, we've long since reached that point. So what? So 0.72 now? Okay, one more doubling. No, one more quadrupling. I said doubling and I meant quadrupling. Alright, so 1024. .817. Yeah, 0.73. 1 second. So yeah. With a large enough workload, we can use parallel programming to speed up, to reduce the execution time. But if the work was too small to begin with, it was small enough to begin with, we don't have to bother with parallel programming at all. So that's one takeaway with parallel programming. When to know when to use it, and if using it has any benefit. I shared a video of using parallel programming to find the seed for a Minecraft world, of all things. And this is a rather interesting project that Minecraft players have taken on, that really tech-savvy Minecraft players have taken on for themselves, and it's basically the essence of the assignment that I had where we brute force the seed for a random number generator, except in the case of Minecraft, you're trying to reverse engineer the world generation for that game to find what seed produced a specific layout of blocks. And people have been successful with these efforts. I've shown the one about finding a tall cactus, but there's also one for finding the seed for a world, but the only image you have is only 128 by 128 pixels. If you're to do this yourself, there's 2 to the 48 power seeds to search for, and that is way too many seeds to look for at any one time. So the efforts of those seed finding attempts involved, among other things, eliminating the possible range of seeds from 2 to the 48 power, which is like 281 trillion, to a more reasonable to a more reasonable size of numbers. So instead of just brute forcing your way through 281 trillion seeds, you use, among other things, parallel programs to eliminate seeds that don't fit this requirement, and basically whittle down the list of possible seeds from a really big number to something more manageable that is like a few tens of millions of seeds. Once you get it down to that size, it's easier to brute force because, well, there isn't much. That's way smaller compared to 281 trillion. And at that point, you don't even need parallel programming. You might not even need parallel programming anymore. You only need it for if you have those really big, just really, really big workloads. Speaking of workloads, I'm not sure if I talked about this, but if you're to go into the field of machine learning, or if you're ever going to do anything with a neural network, one thing to keep in mind is that typically neural networks are, under the hood, just a lot of matrix multiplication. And that is one application I want to get into next week, where I tried to make a matrix multiplication program using NVIDIA CUDA. Yeah, I said I would get into that, but I realized it's way more interesting if I try to show it using NVIDIA CUDA. So that's gonna be for next week. I did have one more main assignment for you though. And it's pretty simple. Can you think of a use case for parallel programming? Or can you think of a parallel programming algorithm that we didn't discuss in class? What I want you to do is write a pretty short paper, just 1 page, describing this use case for parallel programming, or this parallel algorithm that you may find interesting. Be sure to cite any sources you may have. So this is gonna be due tentatively around the 23rd. So you have about 2 weeks to complete this assignment. And then after that, we're gonna, since we're at the tail end of the semester already, I would say that this is gonna be your last main assignment for the course. And then after that, we can look at the final. I will say that the final is going to be take home, but after that, the rest of the details are to be determined. Anyway, this should be available on Canvas soon enough, and with that, I'll end the video here, and hopefully you can see a little bit more of NVIDIA CUDA in action. So, with that, see you next week.